So for the last of our spotlights, we're going to welcome Francesco, who's a PhD student at CISA, which is in Trieste in Italy, to talk about intuitive model selection and decision making. Over to you, Francesco.
Hello, everybody. So let's change topics again. No neurons, no machine learning, and not working. No, okay, it is. We were talking about sensory data interpretation. So animals to survive constantly face decision between competing interpretation for noisy and sparse sensory data. It's an example. We have an animal here, which sees maybe some tracks in the snow, and it can interpret it as just one wolf pack that passed, and maybe now the area is safe, or maybe this area is more than one wolf pack. This is not safe, and it should go away. So how does he do that? This is what we're wondering. The nice thing about this setting and other settings is that the different interpretation can be mapped to probabilistic distribution. You can imagine that for one wolf pack, we have a normal distribution of tracks. With more than one wolf pack, we have a Gaussian mixture model. So having probabilistic model is nice because we can use, we have a lot of theory about selecting between these. So it becomes a model of a problem of model selection. There are a ton of frameworks. We're going to focus on Bayesian model selection. That has a nice feature I'm going to talk about. How does it work? I think you know this formula. And we can use it to predict which model, the probability of the model given some data. So in this example, we would have the model, the path, the wolf pack, and the data is the tracks. And we can have many different models to choose between. And the way this works is just we compute the probabilities. The highest probability is the best one, which is our model. So how do we use this for humans, to understand humans? Let's take this probability. As I said, Bayesian model selection is a nice feature, and there is a very cute, nice approximation of it. It's nice because we can understand what each of these terms are. It's less nice because it doesn't always work perfectly, but we'll talk about that. In terms of the maximum likelihood of the data given the model, the dimensionality of the model, so how many parameters it has, and the volume, which is proportional to the observed information, if you know what it is. Otherwise, ask me in the poster. And what we can do is we can take each of these terms and create a space of how much each of these terms is important for a certain model selection framework. So, for example, this approximation would be where all the three terms are one, and we have the formula I just showed you. But when this doesn't work well, we have a different point for the actual Bayesian probability, and we'll have a different point for other criterion, like bias information criterion or ICAC information criterion. And what we want to do is to find where human model selection sits in this space. So we can represent cognition inside this space. And this allows us to compare different humans, to compare a human to theory, and also in the same person to compare different sensory modalities to see if they do something different or it's all the same. So how do we find these three parameters? We have a very simple experiment. There is some models. One of these models generated some random data, and a subject has to choose which of the model generated this data. And from a lot of answers, we infer the three parameters. In our specific example, in our specific experiment, the models are either one normal distribution, 2, 3, or 4 normal distributions. So the data, let's say we take 2, the data generates, it's something like this. This is what our participants see. And they have to say how many normal distribution generated this. So we did this experiment. For now, it's just a pilot on about 20 subjects. What did we find? These are for the likelihood, for the dimensionality, and for the volume. These are just numbers for you. So let's try to understand what they mean. If we take the approximation I showed you, all the betas are 1, and they do not compare very well. You cannot see this from the line. It's there. Right? But if we take a better, as I said, in the space, there is a better place for the Bayesian probability. And both dimensionality and volume are pretty close. The one that is very different is likelihood. So we asked, why is it different? And the first doubt was maybe likelihood is not very important for humans. But actually, we did a framework comparison where we compared using all three of these terms or using just couples of them. So only likelihood and dimensionality without volume, or dimensionality and volume without likelihood, and only likelihood and volume without dimensionality. And as you see, as you don't see, but when we take out likelihood from theory all the way here, so a way worse model. I'm not going to explain what that ELPD is, but the lower is better. We see this, so likelihood is important. And we also see that volume seems not to be very important, because when we remove volume, nothing changes much. So good thing we use likelihood to understand which model is the best. And we don't use volume as much. So for something like Bayesian information criteria, we don't use likelihood and dimensionality. So let's see how we use dimensionality. For now, we assume that dimensionality is linear as it is in the theory. So the number of parameter and the effective number of parameter is the same, but maybe this is not the case. So what we do is we set these parameters free. They in our inference, they could be whatever, and they got this behavior, which is, I don't know if you can see it, this, they drop a little bit here. So it's a slightly sublinear trend, but it's still very compatible with a linear trend because that error bar is huge. So there is a chance we still behave either as Bayesian information criteria or AIC information criteria, or slightly sublinear, which makes sense because for a big number of parameters, we don't have much of a chain, 55 and 56 parameters, for example. And this is it. If you have questions, no, this is not it. I'm sorry. What we want to do next is we have a point in the space for human cognition, but it's only a visual experiment. What we want to do is repeat this experiment with a different sensory modality. And we want to see if different sensory modalities have different ways to select models. So there are different networks in the brain that select models, or if there is just one central network that selects models. So a centralized cognitive function. And now that's it. Thank you. If you have questions.